All right, guys. So we're going to talk about how to implement iterators for different types of lists. So our Arraylist class contains a private inner class that defines an iterator for the list. So we have an iterator for the list. It's a private class. We talked about this before. They make an argument that using an iterator like this is safe because it has an intimate relationship with the outer class, the collection. I don't know if that's something that I agree with. Well, the iterator class is fine. The way we implement it in the other one is a little odd, but the iterator class is fine. It is implemented by the class itself. So the only way to get an iterator to a particular class or to a particular collection is to use the iterable interface. So it's basically, it's kind of like a factory method. If you take some design patterns, they call it this factory method. So it's a way to get an iterator. It's a way to create an object. It's the only way to create an object, basically. If you want to iterate over a particular collection, the only way to iterate over that collection is to use the iterable interface, right? There's no other way to do it. So in that case, it is, in the sense that for an array list, it is actually reasonable to use iterators. Using it like we were before, where we have an iterator inside of a class and then you pass it up 2 levels, that is a little suspiciously not good. But using it for the class is fine. So again, we maintain a modification count that's initialized to the current number of elements in the collection. If the count gets out of sync, then the iterator throws a concurrent modification exception. So this is an exception because you've changed the container. So you really have to be careful doing this. It's a lot of times it's fairly easy in your loop, but you also have to make sure that, like, if you make a function call inside of like, let's say you're looping over a container and you make a function call, and that function call maybe goes and modifies the container itself, you might get this kind of error. You might also get this kind of error if you're using threads. So you haven't seen threads yet, but you will be using threads soon. If you're using threads, and threads basically let you do things in parallel, so you can have multiple lines of execution. So it's pretty easy in that case for, like, this guy's going through the list, and like, let's say you're writing a game, and this guy's going through a list of all the game objects, and this other guy is going through the list and he's updating the position of all the game objects, and somebody gets shot and you delete one of them and you've changed the container that the other guy is iterating through. You can get this kind of exception. So concurrent modification exceptions happen when that mod count gets out of sync with the iterator. So the iterator has an internal count for what it was when it was created, and if that mod count is different, you're going to get this concurrent modification exception. All right, so here is our Arraylist Iterator, which implements the iterator function. You're never going to make one of these, right? You're always going to, well, you've seen it. You're always just going to get the iterator interface. So, in fact, it's a private class. So it can only be made, well, you know what a private class is. So we have an iterator mod count, which is and then we have an int current. So when we create the Arraylist iterator, we set the iterator mod count equal to the current mod count for the array list. Okay, so it keeps track of that, and then it sets current equal to 0, which means it's going to be basically setting itself at the beginning of the array. So the current is 0, and then the mod count is whatever the mod count was for the array when you created the iterator. So we have this has next, and if you call has next and you've modified the array, then you're going to get a concurrent modification exception. So if the iterator mod count is not equal to the current mod count, you're going to get this exception. It's going to throw this exception. Otherwise, it's going to return current less than rear. In other words, are we at the end of it yet or not? So here is our next function. So we return the element. So this is what I was saying is a little odd. So here's our implementation. So we have our public t next, which throws concurrent mod. So we're going to check and see if something's been modified. So if it's been modified, we're going to toss it out, and that's going to get checked in has next, right? And we're also going to check this. If you called next and there actually isn't a next, we're going to throw a no such element exception. Okay, so there's two exceptions can be thrown. One of them is thrown by has next, but it's not caught in next. So it's going to get thrown up, and we declare that in the concurrent modification exception here when we'd say that it throws it, because we don't plan to catch it here. So you see when we call next, we actually say current plus plus. So we were incrementing basically the index of what we're currently looking at, but then we're going to return the previous element. So it's a little odd, right? So when you delete, we're actually going to have to, when you remove, well, in this case, the remove throws an unsupported operation exception, so we can't remove because it's not operated. It's not supported for this operation or for this collection. So probably this is because it's a pain to delete things in array. You have to shift things. When you shift things, you're going to cause yourself problems, right? So that's why it's not allowed. All right, so you see how this works, and you see how we check the mod count to make sure that things haven't been implemented. So those are the two key things. The key thing here is really how this next works. So we check to see if we have a next one. If we don't, we throw an exception. We increment the current, which remember we set to 0. So this will now be 1, and then we return current minus 1. So we return the previous one related versus the one that we're pointing to now, which is a little odd. When you look at the implementation, you're like, why do they do that? It seems strange, but that's just how it works. All right, so let's look at how you implement this with linked lists. So we can also do the same thing with links. So we're going to have a linked list iterator class, which is implemented as a private inner class. Same thing here. We got this private class, linked list iterator, implements iterator. We're going to have a private int iterator mod count, which is the number of elements in the collection. We're going to have our private linear node t current, which is the current position. Here is our linked list iterator. We're going to say current equals head and iterator mod count equals mod count. So we're going to set the initial thing equal to the head, and we're going to say the iterator mod count equals mod count. So we're setting the mod count because we're going to do exactly the same thing that we did in the last one. So we're going to have a has next. Throws a concurrent modification exception if the iterator mod count does not match the mod count. Okay, so we're going to throw this new concurrent modification exception. I assume that you guys know how the scoping works for variables with private inner classes or with inner classes and private classes. I assume that you know how this works. If you don't, you might go and review that because some of this might make sense. Like, for example, where does this mod count come from? This mod count is the mod count for the containing collection, which this thing can see because it's an inner class, right? All right. So we're going to return current not equal to null because current actually points to the next thing in the list. Again, this is a little odd to get your head around. Current points to the next thing in the list that you're going to return the element for when you call next. So let's go and look at next, and we'll see exactly how this works. So we check has next to see if we check has next to see if we actually have a next, because if we've called next and there isn't a next, we're going to throw no such element exception. Again, we could also throw a concurrent modification exception. Has next is going to check and see if things has been modified. So we get our result from current dot get element, right? So we can get the element out of the current list node. We're going to set current equals current dot next, and then we're going to return the result. So actually, the order of this makes a little more sense than the order of how they did it in the arrays. The arrays look really weird. I wish that they hadn't written it like that because it's a little bit confusing. This makes a little more sense. So basically what your iterator is going to do is you're going to return the thing that you're currently pointing to. You're going to return that element back, the element in the node that you're currently pointing to, and then you're going to increment the node to point to the next node. So if you're at the end of the list, let's think about it. If you're at the end of the list, then current is going to be null because current points to next is going to be null. So current is going to be null. So that's why we check here. If current is not equal to null, there must be a next element in there because the next element is the thing that current currently points to in this implementation. All right. So this is a little bit strange, but again, if you think about it, it makes sense. So this is the internal implementation for iterators. If you plan to implement iterable classes, you're going to have to do this. A lot of times you're just going to use these things. In this case, we're gonna throw this unsupported operation exception because we're not going to support remove. That's just a choice. We could support remove. It's not a problem, but they're just not implementing because they're really interested, I think, in showing you the next and the everything else. So that is the end of the lecture. Thanks, everybody.